Hi, advanced math topic students. This is my first Camtasia video in a while, so it may be rough, but I'll do the best I can. First, an announcement. If you are on Canvas and are not sure how to submit homework, send an email to Peter, Victor, or James. I sent everyone an email with their addresses. So that's the first thing. Then I'm going to go to some definitions. So, sorry, that's not the one. See, I told you it was going to be rough. There we go. So, these are some important definitions, and this is part of a list that I had from last year that I will update. But you will help me by making definitions for the three basic transformations, the three basic isometries. So, what are those things? A transformation of the plane is a one-to-one mapping of the plane onto itself. So, the domain is the entire plane, and the range is the entire plane. That's important. On isometry, the word tells you what it is. Iso is same and metry is measurement. So it's a transformation that preserves distance. That's the definition. And preserves, you'll see in the one of the homework documents, just means that if the distance between 2 points in the pre-image, let's say, is 5 inches, then the distance between the two image points is also going to be 5 inches. I don't want reflection yet because I want you to come up with that. An equivalence relation is needed, I think, to precisely define vector, and I haven't seen that really done that way in many high school books. But an equivalence relation, and I'm indicating it with three horizontal lines, an equal sign with an extra one, but it can have any symbol that you want. It's a relation on the set S is an equivalence relation if it is reflexive, symmetric, and transitive. And you can see what those mean. Reflexive just means any member of the set is equivalent to itself. Symmetric, if x is equivalent to y, then y is equivalent to x, backwards. And transitive means that it goes through, sort of. So if x is equivalent to y and y is equivalent to z, then x is equivalent to z. You know a number of equivalence relations already, in addition to equality. And it would be useful for you to think of some geometric or numeric, number theoretic equivalence relations. And I'll ask you about that in class. An equivalence class, if a set has an equivalence relation, then there are equivalence classes. And an equivalence class is more or less the maximal subset of members that are equivalent to each other. That's really the easiest way to say it. I tried to say it more precisely here, but that's what it is. And that's useful in defining a vector. You know, a vector is kind of this strange thing that can move around. How do you define it precisely? So a vector AB, and that's the symbol for it with an arrow over it from A to B. A is the initial point, B is the end point, is an equivalence class of directed line segments that are equivalent to the one from A to B under the following equivalence relation. Two directed line segments are equivalent if and only if one is a translation image of the other. So you sort of need to define translation before you define vector, I suppose. So we'll talk about that in class. I may modify this. You know, this is my first try at it, so think of it that way. The canonical, which means most convenient, representative of each equivalence class has its initial point at the origin. And if we have vectors with, if we think of vectors with initial point at the origin, then that enables a correspondence between vectors and points in the plane. Okay, the endpoints of vectors from the origin. That's the correspondence. So if we make the initial point the origin, then the endpoints specify each vector. Notations for a vector that goes 2 to the right and 3 down, for example, is one way to think of a vector, the rectangular way. So one notation is a less than and a greater than sign, sort of, except instead of parentheses, 2 comma negative 3. Another is 2i minus 3j, where I is a unit vector in the positive x direction and j is a unit vector in the positive y direction. I did that a lot, actually, when I was teaching. We used that. So twice a vector means you scale it. You multiply its length by 2, but you keep its direction the same. Some books use just 2, negative 3 for a vector, but that's easily confused with a notation for a point, so I personally don't like that. So one of those others is better, and you can tell me in class whether if you have a different notation. And we'll think about this. Think of this as a preliminary definition, and maybe we can modify it and make it a little better. Okay, that's in addition to the announcement, that's the second thing I want to do, and I want to do just one more thing, actually, and that is to go to GeoGebra and make a rectangle, a dynamic rectangle, and illustrate that the way I'd like it. So I want the screen to just have a rectangle that moves around and is always a rectangle. And I'm going to ask you to do the same thing or a similar thing with an isosceles trapezoid. So to make a rectangle, we might start with a segment that doesn't have to be horizontal. So let's make it this way so it doesn't have to be. And then we want to use the perpendicular line tool, but we need to make a point first, as we see. So no, I'm going to use the endpoint. So it says select a point and a perpendicular line. So I'm going to select the endpoint and this line. Okay, and there's my perpendicular line. Now I want to select a point on that line, say here. And then the next thing I want to do is, now there are lots of ways to do it from here. You can make a parallel or a perpendicular. Let's practice the parallel line tool. So I'm going to go here for parallel line. And the parallel line is I have to select a point and a parallel line. So I'm going to select this point and this line. And then I'm going to select this point and this line. And then I want to make a point on the intersection. And just to do it a different way, I could just take the point tool and put it on that point. But another way to do it is to use the intersection and then select the two lines that I want to intersect, and there's the point. So there are many ways to do it. Now, you might think that you're finished, but you're not, because this has other things in it that we don't want. So what we're going to do is hide, and the easiest way to do that is to right-click or control-click and show object, uncheck, basically, show object. So I'm going to hide all the lines in the figure. Okay. And now I'm going to use the segment tool, which is here, and connect the points. So there's one, there's another, there's another. This is a rectangle. If I wanted to measure its area, I could use the polygon tool with those points and make it that way. I would like to label my rectangle, at least the points. So I'm going to show, sorry, I want to show the label. So there's A on show the label. Now I may not like the order in which I did the points, because usually we go around, we go around the figure. And here it's A, B, D, C instead of C, D. Now I'm not going to be able to change D to C right away because C already exists. But I could use a programming trick, which is to rename this first as E, a different one. Okay, and now I can rename this one as D. It's down here. I'm right-clicking to get that. Name this one as D. And then I can go back and name this one as C. And now I have A, B, C, D. If I want to move the labels as well as the points, I can move them. But is this really a dynamic rectangle? Well, we have to test. If I drag it this way, it's still a rectangle. If I move this, it's still a rectangle. Different things will happen depending on the construction that I used, as you can see. The points drag differently because of the different constructions I used. And I can't drag C because C is a child of parents. In other words, C depended on the other points. Obviously, I couldn't drag C also because it wouldn't be a rectangle if I could just move C. So no matter how I move this, and is this no? I can see you have to do the control point. So that gets some getting used to. What I have to drag is just the early parts of the construction, so that the later parts depend on it. So the best points to draw, if I want it to be as dynamic as possible, are the first 2 points that I made, A and B. Those are the parents of this, and no matter how I move it around, it's a rectangle. So there's a dynamic rectangle. Okay, that's it for today. Let me go back to Camtasia and stop the recording, which is